Assalamualaikum and hi everyone. Today we will be presenting about the metallic bonding. In this video, we will learn on how to identify metals using the periodic table, explanation of models of metallic bonding and band theory, the key properties of metals, and lastly, the real-life applications of band theory. So, what is a metallic bonding? A metallic bond is the force that holds atoms together in a metal. It is caused by the attraction between positive metal ion and a sea of delocalized electrons that move freely throughout the metal. This attraction forms strong bonds between the atoms. The strength of a metallic bond increases with the number of delocalized electrons and decreases as the size of a metal atoms increases. Here is an example of a metallic bonding. This diagram shows a metallic bonding. The red circle with plus signs represents positively charged metal ions which are fixed in a regular lattice. These small blue dots with minus signs are delocalized electrons from the outer shell of the metal atom. These electrons are free to move throughout the entire structure, forming a sea of electrons. The strong attraction between the positive metal ions and delocalized electrons hold the metal atoms together and creates the metallic bond. This explains why metal can conduct electricity and are malleable and strong.
Next, we are talking about model of metallic bonding, which is the electron C model. So what is the electron C model? The electron C model explains metallic bonding by describing metal atoms as positive ions surrounded by a sea of delocalized valence electrons that move freely through the metal lattice. We need to understand that the valence electrons are free to move. They are said to be delocalized. So what is that means of delocalized? These electrons can move and share among many atoms so that it gives the metal of electrical conductivity. However, metal atoms become positive ions. These free electrons are attracted to the positive metal ions, thus creating a bond. For example, when the electrons leave the atom, it creates a positively charged ion. Then, these delocalized electrons creates the negative cloud that attracts to the cation, and these cations are able to attract to each other through this cloud of electrons, which they are forming a strong metallic bond. As you can see, the picture of metal shows this arrangement of metal lattice in a piece of metal. Lastly, the metal's atoms that become positive charged ions when the electrons are free moving delocalized. I will explain how the electron C model occurs, and let's consider that this aluminum metal. From the arrangement of the aluminum atom, it consists 13 protons and 13 electrons around protons, and 4 the outer shells have 3 valence electrons. These 3 electrons are loosely held, resulting detached from the atom and move freely through the structure. This leaves remaining core with positive 3 charge of each aluminum atoms. Then the delocalized electrons are create a sea of electrons surrounding the positive cores. They are also strongly attracted to each other and holds the atoms together in the lattice. This is the reason why that electrical conductivity happens. The limitations of simple metallic bonding models. First is they are assumed all metals as the same. Every metal has different properties. For example, tungsten have extremely high melting points, whereas mercury are liquid at room temperature. Second, the limited explanation of electrical conductivity, which each metals have a different conductivity. Conductivity also can affect due to change with temperature. Lastly, oversimplified electron behavior. Electron acts as free moving in the structure, but it still interacts with metal ions and other electrons, so this ignores the effect, interactions of conductivity and bonding strength.
Moving on to band theory. When valence electron receive energy from external sources, it can jump from valence band to conduction band, and then only it will conduct electricity. Conduction band is a higher energy level in solids where electrons are free to move, enabling electrical conductivity. The amount of energy that electrons needed to jump is called band gap. There are 3 types of material with different conductivities. The first one is insulator. As you can see in the video, there is a huge energy gap between the valence and conduction band. Because of this large band gap, electrons do not have enough energy to jump from the valence band to the conduction band, so it does not conduct any electricity. The second one is semiconductor. Normally, only atoms with partially filled valence band can conduct electricity. But in this case, semiconductor consists of fully filled valence band that can moderately conduct electricity. But how? As shown in the diagram, the band gap is much smaller than insulator. In semiconductors, electrical conductivity depends on the Hall current. Increasing temperature increases the conductivity by providing thermal energy that excites electrons across the band gap, creating a Hall current, making it conduct electricity. So here is the way how Hall current is formed. When electron jumps to conduction band, a vacancy is formed when it receives energy. The electron that remains in the valence bond will move in the vacancy. This movement produce a current in valence bond, which what we call as a Hall current. Lastly, in conductors such as copper, there is no band gap. Actually, the valence and conduction bands are overlapping between each other, which means electrons can move freely to the conduction band. This is why you may hear the term sea of electrons, which only means they are just moving around. In conductors, electrons receive energy from the applied electric field, while decreasing temperature reduces collision, thereby increasing conductivity.
This slide, I will explain the conduction property of metals. Metals are good conductors of electricity and heat. This is because their atoms contain delocalized electrons. These electrons are free to move throughout the metal structure. When heat or electricity is applied, the electrons transfer energy quickly from one area to another. As a result, metals are widely used in electrical wiring, electronic components, and heat transfer applications. So, melting and boiling points. This slide shows the melting and boiling points of metals. Most metals have high melting and boiling points. This is due to strong metallic bonding in their structure. Positive metal ions are held together by strong electrostatic forces with delocalized electrons. A large amount of energy is required to break these forces. Therefore, metals can withstand high temperatures and are suitable for industrial and structural uses. This diagram explains malleability. Malleability means a metal can be bent or hammered into shape without breaking. In pure metals, the atoms are arranged in regular layers. When force is applied, these layers can slide over each other, so the metal changes shape instead of breaking. However, in alloys, there are different types of atoms mixed together. This makes the structure less regular, so the layers cannot slide easily. As a result, alloys are usually less malleable than pure metals. This picture shows the lustrous appearance of metals. Most metals are shiny, and this property is called luster. Metals look shiny because they have delocalized electrons on their surface. These electrons can move freely and reflect when light hits the metal. The reflection is what makes metals appear bright and shiny, which is why metals are often used in jewelry and decorative items. This slide explains real-life applications. For electrical wires, metals like copper and aluminum are used because they have good electrical conductivity. They are also ductile, which means they can be drawn into thin wires. For cooking utensils, metals conduct heat well. This allows heat to spread evenly, making them suitable for pans and pots. Lastly, for structural materials, metals are strong and malleable. They can be shaped into various forms and are commonly used in construction.
Conclusion. To conclude, metallic bonding occurs when metal atoms form a lattice of positive ions surrounded by the localized electrons. These free-moving electrons are what hold the structure together and give metals their characteristic behavior. The electron-C model helps explain general properties like malleability and conductivity, but it cannot explain differences between metals. Band theory improves this by showing how overlapping or partially filled energy bands allow electrons to move freely and conduct electricity. Overall, metallic bonding and band theory together explain why metals are good conductors, have high melting points, are malleable, and appear shiny.